The right triangle altitude theorem says that when you have a big right triangle with an altitude drawn to its hypotenuse, three similar triangles are formed. The original big right triangle and the two smaller right triangles are all similar to each other. First, we're going to take the big right triangle and the two smaller right triangles, and we're going to redraw them so that they're facing the same way, and we can see which parts correspond from the three different triangles. So what we're going to do first is we're going to redraw the big right triangle. So in the big right triangle, the right angle is at B. So I'm going to label the right angle with B. I'm going to imagine that I'm taking the big right triangle and rotating it up so that the right angle is in this position. So I'll put C at the top, and that leaves point A to be over here. Next, I'm going to redraw the smaller right triangle on the left. In this smaller right triangle, the right angle is at point D. So I'm going to put point D over here. Since this triangle is inside of the big right triangle, it shares an angle with the big right triangle. The angle that it shares with the big right triangle is angle A, because angle A is in this triangle, and at the same time, it's also in the big right triangle. So if we put angle A here in the original big right triangle, it's got to be here in the blue triangle, because if it's a shared angle, it has to correspond to itself since it's congruent to itself by the reflexive property. And that leaves point B to be over here. Finally, we're going to redraw the other small right triangle that I outlined in green. Once again, the right angle of this triangle is at point D. And just like with the blue triangle, the green triangle is inside of the big right triangle, so it has a shared angle with the big right triangle. And this shared angle is angle C. Angle C is in the small triangle, and at the same time, angle C is in the big right triangle. So since we put angle C up here in the big right triangle, it's got to be in the same spot in the green triangle since it's shared between the two triangles, so it's congruent to itself by the reflexive property. And that leaves B to be over here in the green triangle. Now we have all three triangles redrawn so that they're facing the same way. Next, we're going to do some labeling. So in the big right triangle, the hypotenuse is side AC because it's across from the 90-degree angle. So I'm going to label side AC as H for hypotenuse. And that means I need to label this as H because this is AC. I'm going to label this side and this side of the big right triangle as legs, because when we have a right triangle, we have the hypotenuse, and the other two sides are called the legs. So I'm going to call this leg leg 1, and I'll call this leg 2. So leg 1 is AB, so that means that I have to make this L1 and this L1, because these are AB in the separated triangles. And BC is L2. So let me put that into my separated triangles as well. We're going to label the altitude drawn to the hypotenuse of the big right triangle as A for altitude. So I'm going to call BD A for altitude. There we go. And finally, notice how the altitude splits the hypotenuse into two segments, AD and DC, two different parts. So we're going to call AD segment 1 of the hypotenuse, and we're going to call DC segment 2 of the hypotenuse. So AD is going to be segment 1, and DC is going to be segment 2. And now everything is all labeled. Now, since we know all three of the triangles are similar to each other, according to the right triangle altitude theorem, we can make some important proportions. The first proportion that we're going to make is going to involve the legs of the big right triangle. And there's going to be two proportions that we're going to make for the legs. We're going to make one for leg 1 and one for leg 2. And essentially, they're going to be the same, just with one tiny difference. Now, I'm going to start with the big triangle and the middle triangle over here. So I'm going to start with H, side CA, which is H, the hypotenuse. And it corresponds to L1 on this middle triangle. They're on the same spot on the two different triangles. And I'm also going to use this side from the big triangle. And that corresponds to this side on this triangle. Now I'm going to make just one more proportion, and then we'll talk about these. And my other proportion is going to have the other leg, L2, in it. Notice how this one has L1 in it. And we're going to make it using the big right triangle and the other smaller right triangle. So once again, I'm going to use side H, the hypotenuse. And that corresponds to L2 on this triangle. And now I'm going to use this side from the big right triangle, which is L2. And that corresponds to this side, which is S2. And here, these two proportions are what we call the leg rule. Here's where they come from the corresponding sides of the similar triangles. Now we'll talk about what they do. So the leg rule says that each leg of a right triangle is the mean proportional. That's just a fancy word that means in the proportion, the leg gets written twice so that when you cross multiply, it gets multiplied by itself. So the leg of the big right triangle is the mean proportional between the whole hypotenuse. Notice that there's H in the proportion. And the part or segment of the hypotenuse directly below that leg. Notice in the proportion that involves leg 1, the segment is the one directly below that leg. Notice how in the proportion that involves leg 2, the segment being used is the one that's directly underneath that leg. You can remember the leg rule because the proportions look like the word hill, and there's two of them. So we can call this hills. So throughout the video, you'll hear me referring to the leg rule as hills. So in order to find a leg of the big right triangle, all you have to do is substitute in the length of the whole hypotenuse, H, and the length of the segment that's directly underneath the leg that you're using. I'm going to come back over here, and we're going to set up one more proportion involving the corresponding sides of the similar triangles. The next proportion I'm going to set up involves the two smaller triangles. Now I'm going to start with this side of this triangle, which is labeled as S1. And that corresponds to this side of this triangle, which is the altitude. Then I'm going to use this side of the first triangle, which is the altitude. And that corresponds to this side, which is S2. And here we have another rule that comes from the proportions with similar triangles. And this is the altitude rule because it has the altitude in it. And what the altitude rule says is that the altitude drawn to the hypotenuse of the big right triangle is the mean proportional. Once again, all that means is that in the proportion, it gets written twice so that it gets multiplied by itself. It's the mean proportional between each segment of the hypotenuse, each part of the hypotenuse. So we use the altitude rule when we either are finding the altitude or when we have information about the altitude, when you have the measurement of the altitude already. If you don't have any information about the altitude, and if you're not looking for the altitude, if the altitude's completely unknown, then you're going to be using the leg rule. So SAS, I forgot to mention, the way of remembering this is SAS because it looks like the word SAS, except with two A's instead of two S's. So SAS is for when you have information about the altitude. Hills is for when you don't. When you don't have the altitude, use the leg rule, use hills. Let's see some examples. In this first question, we need to determine the distance across the lake. And we have a big right triangle with an altitude drawn to the hypotenuse to create two smaller right triangles. Exactly the situation we had here. So we're going to ask ourselves, is this going to be hills or SAS? And in order to figure that out, I'm going to ask myself, do I know anything about the altitude? And the answer is yes, I do. I know that the altitude is 6. So I am going to be using SAS, which is the altitude rule. So I'm going to write down SAS, and now I'm going to plug in. S is the two segments of the hypotenuse. So that's 4 and X. And the altitude is given to us as 6. And now we have our proportion set up using the altitude rule, using SAS. Cross multiply. We have 4x is equal to 36. So x is equal to 9. So the distance across the lake is 9. Moving on to the next one. It says determine the length of GHHK. GH is a leg of the big right triangle. Remember, the hypotenuse is opposite from the 90-degree angle. So this 32 side GK is the hypotenuse. So that means GH and HK are both legs. Since I'm looking for a leg, and since I don't know anything about the altitude, this is going to be a hills situation rather than a SAS situation. So let me plug in for hills. H is the hypotenuse of the big right triangle, opposite the 90-degree angle. GK, which is 32. The leg I'm looking for first is X. And for the segment, we're going to use the one directly below the leg that we are finding. Let's cross multiply. And when we cross multiply, we get 256 is equal to x squared. So if we take the square root of both sides, we have x is equal to 16. So that represents the measurement of GK. Now we just need to find HK, which is the other leg. I'm going to represent it as Y. Once again, we're finding a leg of the big right triangle, so we're going to use hills. We're going to use 32 for the hypotenuse because the triangle didn't change. So the hypotenuse of the big right triangle is still 32. This time, the leg that we're solving for is Y. And this time, we're going to be using the segment that's underneath the leg that we're finding, which would be 32 minus 8, because 32 is the whole hypotenuse. and that would be 24. So now if I cross multiply, I get 768 is equal to y squared. That does not work out evenly when I take the square root. So I'm going to write this in simplest radical form. In simplest radical form, this would be 16 radical 3. Moving on. Now we're going to take a look at some regions questions. Over here, we have the same situation as before, where we have a big right triangle with the altitude drawn to its hypotenuse. And we're finding which lengths would not produce an altitude that measures 6 radical 2. So since it mentions that we're finding the altitude of 6 radical 2, we're finding which would not produce an altitude of 6 radical 2. But since we are looking for the altitude, we're going to be using SAS here, not hence. So what I'm going to do is I'm going to try out the answer choices. In answer choice 1, AD is 2, DB is 36. Let's find what X is. So SAS, the segments are 2 and 36. We're looking for the altitude. So we have 36 times 2 is 72. And simplest radical form, let's see what radical 72 is. And that is 6 radical 2. So that's not the answer choice that we're looking for. And if you have trouble simplifying the radical, you can just type 6 radical 2 into your calculator and see what the decimal is. And then you can type radical 72 into your calculator and see if it's the same decimal, since this is a multiple choice question. Let's edit this slightly, or answer choice 2, because answer choice 1 was not correct. It did make an altitude of 6 radical 2. Answer choice 3 has the segments as 3 and 24. So that would slightly change our proportion, because now the lengths of the segments changed. So we have 24 times 3, put that 72. So it's going to be exactly the same as the first one. So that's not the answer choice that we're looking for either. Okay, let's reset and let's try out answer choice number 3. That's 6 and this is 12. Let's edit our proportion and let me cross multiply. 6 times 12, and look, that's once again 72, so this is going to be the same exact thing. So that leaves us with answer choice 4. And just to show you why, if I reset and I put 8 and 17 and I redo my SAS proportion and I cross multiply, that's not 72 this time. That's 136 is equal to x squared. If you put in radical 136 into your calculator and see what the decimal is, it's not the same decimal as if you were to put in 6 radical 2. These are not equivalent. Over here, we're told that we have triangle PQR, where angle PRQ is a right angle, and RT is drawn perpendicular to hypotenuse PQ. If PT is X, RT is 6, and TQ is 4X, what is the length of PQ? So we need to ask ourselves, hills or SAS? And we know the altitude, so this is SAS. The two segments are X and 4X. and the altitude is 6. Cross multiplying, we have 4x squared is equal to 36. If we divide by 4 on both sides, x squared is equal to 9. So we have x is equal to 3. So that means PT is 3, and TQ is 4 times 3, which is 12. So the whole length of PQ would be 15. Notice how the x value was an answer choice, but it wasn't the correct one. Make sure you read the questions carefully. We're going to do a few more examples. In this one, we have the same situation, big right triangle with an altitude drawn to its hypotenuse. And we're told that SQ and QR are in a ratio of 1 to 4. So I can represent SQ as 1x, and I can represent QR as 4x. And we're looking for the length of SR. Let's ask ourselves, hills or SAS? And we do have information about the altitude, so we're going to use SAS here. So our two segments are 1x, or just x for short, and 4x. And our altitude is 8. Cross multiply, we have 4x squared is equal to 64. If we divide by 4, we have x squared is equal to 16. That makes x equal to 4. So that means SQ is 4, and QR is 4 times 4, which is 16. So together, 16 plus 4 is 20. So the length of SR is 20. Once again, make sure you read the questions carefully. 4 streets in a town are illustrated in the diagram. This big right triangle with an altitude drawn to the hypotenuse. I'm going to think hills or SAS as I'm reading. If the distance on Poplar Street from F to P is 12 miles, and the distance on Maple Street from E to M is 10 miles, find the distance on Maple Street from M to P. So I'm going to ask myself, hills or SAS? Do I know anything about the altitude? No. Am I looking for the altitude? No. I'm looking for the segment of the hypotenuse. So this is going to be a hills situation because we don't know anything about the altitude. So H represents the entire hypotenuse of the big right triangle, which is the 10 part plus the x part, 10 plus x. The leg that we have information about is 12. And for the segment, we use the one directly below the leg that we're using. Remember to distribute 10 times x is 10x. X times x is x squared. 12 times 12 is 144. I'm going to reorder these. X squared plus 10x. I'm going to subtract 144 from both sides. And notice I have a quadratic. So I am going to have to factor this. So I'm looking for two numbers that multiply to give me negative 144 and add to give me 10. Take a second, pause the video, and think about two numbers that multiply to give you negative 144 and add to give you positive 10. If you were thinking 8 and 18, you are correct. Positive 18 and negative 8, because 18 times negative 8 is negative 144, and 18 plus negative 8 is 10. So we have two solutions here. x equals to negative 18, and x equals to 8. But we're talking about a real world object. We're talking about streets in the question. And if we had negative street lengths, distances, that wouldn't make any sense. So we reject the negative, and the distance that we're looking for is 8. Finally, we have one more example, and we have right triangle RSU, and UT is the altitude drawn to hypotenuse RS. The length of RT is 16 more than the length of TS. So I'm going to label TS as X because I don't know what it is, and RT is 16 more than X. And it also tells us that TU is 15. And it says find the length of TS in simplest radical form. Find the length of RU. So we're finding two things, TS and then RU. So first I'm going to ask myself, Pilzer says, I have the altitude, so that's going to be SAS. One segment is X plus 16. The altitude is 15. And the other segment is X. Cross multiply, we have X squared plus 16X is equal to 225. If I subtract 225, x squared plus 16x minus 225 is equal to 0. I'm going to have to factor again. I'm looking for two numbers that multiply to give us negative 225 and add to give us positive 16. Pause the video and try to see what those two numbers are. Those numbers are 25 and 9. Positive 25 times negative 9 gives you negative 225. And positive 25 plus negative 9 gives you 16. We have two solutions, x equals negative 25 and x equals to 9. Once again, since we're talking about a real world object, a shape that you can see, it doesn't make sense for it to have negative side lengths. Then you wouldn't be able to see it. So our x value is 9. So let's find the length of TS. Well, that's x. So that is 9. Now we need to find the length of RU. I'm going to label that Y. And that's a leg of the big right triangle. So that's going to be hills. Before that, I'm just going to plug my x value into RT to see what the whole hypotenuse is. So 9 plus 16 is 25. So the whole hypotenuse is 34 because 25 plus 9 is 34. So now I'm going to set up hills to find RU. The whole hypotenuse is 34. The leg that we're looking for is Y. And we're going to be using the part of the hypotenuse segment that's directly below that leg. That's 25. From here, we can cross multiply. We have 34 times 25, and that's 850, is equal to y squared. We do need to put this, according to the question, in simplest radical form. And in simplest radical form, that would be 5 radical 34.